All right, guys. So in this lab, we are going to be um, learning about resistivity of the material. So we're going to do an activity that will help you understand and investigate the resistivity of material, in this case, a graphite. So resistivity of the material is related to the resistance of the material, and the resistance and resistivity are not exactly the same thing. So for example, let's assume that you have some kind of a wire, and this wire has length L, and it has a cross-sectional area A. So let's say this is some kind of conducting wire. And one of the things we have here is this wire has a lot of, let's say free particles that are randomly moving, within the conductor. Okay. So then one of the things I can do here is when I connect this to a battery, for example, right? If I connect it to a battery, it means the both ends, let's say this is point A and then this is point B. So if I connect it to the battery, then as soon as I do a connection, there's a current. So remember, there's an electric field, right? Which basically then, so let's talk about first electric field, right? So there's a like electric field in the circuit, which is from the positive terminal, starts from the positive terminal, goes back to the negative terminal. So then let's assume that also there's this electric field within my conductor and all the way back to the negative terminal. As soon as you have electric field inside that, that conductor, right? This piece of wire, this conductor, then those electric fields exert force on those charges inside the conductor. And all of those charges now collectively moving in the same direction. So this collective motion of those charges then is defined to be the current, right? So then the current is defined the flow of those charges. Now, depending on what type of system you have, most of those charges that are moving and we use them to define current are actually electrons, and they always move in the opposite direction of electric field. So technically electrons will be moving in this particular case counterclockwise. But to simplify, we use what we call conventional current, and we define that to be, let's assume those charges over there are positive charges. Then the electric field will push them, in the same direction. So then what we can say here is the direction of electric field is basically same direction as the current. So now instead of using this electric field, we can say then there is this current I in the circuit. And for example, again, if I choose some kind of cross-sectional area A within my conductor, then the current here is defined how many charges going through that area of that conductor as a function of time. Okay, that means again, it's the same cross-sectional area A, right? So basically the flow of charges through that cross-sectional area A. That's what the current is. So it's defined as the delta Q over delta T, the rate at which the charge is moving through that, through that area A. Now, this current is proportional to the voltage that we provide between those points A and B. Well, that voltage between points A and B is basically same as the voltage of the battery. Okay, because see, points A and B directly connected to the terminals of the battery. So then this voltage, between points A and B is exactly same as the battery. Doesn't always have to be, but let's say in this particular circuit that I have, it is equals to. But think like this: the current through this conductor is proportional then to the voltage. Let's call this AB between points A and B. Now, that means if I dial the voltage up, which basically there's a power supply, right? I make it basically a more voltage. Which think like this: if this is a battery, think like this: those double A, triple A batteries. So think like this: this is 1.5 each double A battery, right? See, if I put another battery like this, so 1.5, 1.5. So then technically what I have here is I have 3 volts battery. That's how I can make technically the battery, provide more voltage. So that's why sometimes you need to put the batteries, together like this, right? Or next to one another. And each one is, gives you different amount of voltage depending on, let's say, what we want. Anyway, so think like this. The current is proportional to the voltage, means that if I increase voltage, the current in the wire then increases. But what we also have is that current can also be controlled by the material itself, because the material can also provide some kind of resistivity or resistance to the flow of those charges. That means current is then inversely proportional to what we call resistance of that wire. Now, resistance of the wire is basically represent, so like, let's say, remember, those charges are moving, right? Now, as those charges are moving, they're colliding with each other and things like that, and also represents how well this, this piece of wire, right, this material here is, like keeping its, molecules, or, let's say the atoms, right, close to one another. So basically things like this, depending on what type of material we have, each material have different resistance, or it can provide different amount of resistance to the flow of charges. And the current is inversely proportional to the resistance. That means if this wire has a large resistance, then the current technically will be lower than before. That means the charges will not be moving through that wire as freely as they would. And that's pretty much the basis of the Ohm's law, which we'll also explore in the future labs. That means the current here is equals to voltage over the resistance, where it's directly proportional to voltage in inversely proportional to resistance. That means if you want more current, then you have the wire, this piece of wire, you want it to be less resistance, provide less resistance to the circuit. If you want to control and have less current in your circuit, then you want to put something that has large resistance, and it will lower the value of the current in your circuit. In a way, this is one way that you can control how much current goes into the circuit, because some appliances, like some devices, cannot handle too much current. They can, let's say if it's a light bulb, it can blow the fuse, right, if too much current goes. So then you put a little bit of resistance over there, and then it controls, basically lowers the value of the current in your circuit. So that's kind of like what the resistors as a device, right, responsible for, kind of controlling the amount of current in your circuit. So if you want more current, you lower the resistance. You want less current, you increase the resistance in your circuit, and with that you control. Now, generally what we have is this. So the voltage is basically what we get from the battery. The current, remember that other experiment we did where you can put a like ammeter and measure the current? So that means I can put like a voltmeter here to measure the voltage across A and B, and ammeter over there, right, to measure the current, and I can calculate the resistance value as the ratio of voltage over the current. Okay, so ratio of the voltage over the current. Now, for example, if I have 10 volts, let's say this voltmeter measures 10 volts, and let's say ammeter measures 5 amps. Okay, then what I can have here is, again, I'm just making up those numbers. So 10 volts over 5 amps, then I get 2, the units are ohms. Then what happens if I, for example, have 20 volts? What will be then resistance? Would the resistance value change? Well, if I do 20 volts divided by the current, remember the current is directly proportional to voltage, which means that if I double the voltage, the current doubles. That means now the current that ammeter measures will be 10 amps, which means that if I do that ratio, I'm going to get 2 ohms. And that will be pretty much always. If I, lower the voltage into, let's say, I don't know, let's say instead of double it, I make it half, so 5 volts, and then current right away will be affected by that because it's directly proportional. So instead of 5 amps that we started with, it will be then 2.5 amps, which means again we're going to get 2 ohms, which means the value of resistance you can see here seems to be completely independent of how much voltage and current we have. And it is indeed independent of the current and voltage, because resistance is actually property of the material itself. So if you have the material, how much resistance you have in the circuit is not dependent really on voltage and current. You can calculate it by using, measuring the voltage across and the current going through and then find it. But technically its value is fixed. That means if I take that, piece of wire and remove and just put it right now like this in front of me, the resistance will still be 2 ohms, because the resistance is basically measured or calculated because of the geometry of the wire itself. It is directly proportional to the length of the wire. So let's say length of the wire tells us by, you know, uh, let's say it gives us information about the resistance. Longer the wire, more resistance it actually has. Shorter it is, less resistance actually provides to the circuit. Then that means it's a direct proportionality. If I double this, I double that. Now, it also related to the cross-sectional area, but it's inversely proportional to cross-sectional area. That means if I make the area bigger, then I'll have more charges can, go through that, area. That means it's inversely proportional to the resistance. I make the area bigger, charges then have more charges going through, then resistance decreases. So this is how the resistance then related to the geometry of the wire itself. The length directly proportional to the resistance, area is inversely proportional. Now, what we do here is then if we go from proportionality sign to equal sign, then I can say this is then equals to L over A, and then we introduce a constant. And that constant here is then this what we call resistivity. So rho is the resistivity of the material. Okay, resistivity of the material. So the units are, if you look at this equation, right, it's some rho constant times L over A. Well, L has units of meters, A area has meters square. So then technically this ratio together gives you 1 over meters, right? But look at the left side. The left side is resistance, and it should be in ohms, which means that the combination of resistivity and the ratio of the length and area should also give you the, resistance as ohm, right? That means resistivity has the units of ohms times meters. So then this meters cancel out, and then you have just ohms. That means units for the resistivity is ohms times meters. Now, what is then the difference, sort of like, let's say, physical, difference between resistance and resistivity? Well, take it like this. Resistivity represents some specific information about the type of material we have. Okay, so resistivity is very specific to type of material. Resistance is then very specific to this particular wire. Okay, so for example, let's say this material is copper. For example, let's say it's copper. All right, so then resistivity of copper, right? Resistivity of copper is then equals to 1.72 times 10 to the negative 8 ohms times meters. Okay, so this is the units for the resistivity of copper. Now, it doesn't matter what my wire looks like. Could be something like this, could be something like that, could be something like this, could be something like that. Resistivity of every single copper wire is exactly that. Then how about the resistance of a copper wire? Well, now resistance is different depending on the type of wire I have. So resistance depends, remember, on length. That means, longer copper wire has a greater resistance. Shorter copper wire has a, lower resistance. Bigger area copper wire has a, lower resistance. Small area has a large resistance. That means it's equals to resistivity, which is same for all the copper wires, but then length and area of the copper wire, specific copper wire, right? Then you can give us the resistivity of that. That means, for example, specifically for this one, its length and area then will determine how much resistance it has. Resistivity is the same because it's, let's say it's a copper wire, but the resistance not the same. Let's say if I cut it in half, for example. If I cut it in half, then resistance is exactly half what it was before, right? Because, I'm doing this is 1/2. That means this is also 1/2, but the resistivity doesn't change. And that's what we're going to be then going to try to find. We're going to then relate our experimental result to this particular equation. That means we're going to say, okay, so we have let's say an object. So let's say this is our object. So we know that resistance is equals to resistivity times length over area. Then if we use a device that is known as a ohm meter. So ohm meter is a device that measures not the voltage or current, but the resistance. Remember, that device that we have that is known as a multimeter can technically measure voltage, current, or in this case also resistance. All right, so let's say we have an ohm meter, and let's say we take the ohm meter and we connect to points A and B, and let's say we measure the length A and B. Okay, and let's say we know that, or we provided with the cross-sectional area. Then what I want to do here is we're going to take data to see if this relationship is correct or true or not. Basically, investigate, verify that. That means, for example, if I have ohm meter and the symbol for the ohm meter is like this. If I connect to points A and B, and then I say, all right, so here's my data table. This is then resistance, and let's say this is the length. So when the length here is, let's say, I don't know, let's say LAB, for example, what is then the resistance? And the resistance is directly from the reading of the ohm meter. Then we move the probe, let's say, to somewhere over here. So at some point C. I say, okay, so this is length LAC. That means from A to C. What is the resistance? Let me do it like this, right? So resistance of AB, then resistance of AC. And then again, we continue, we move the probe somewhere over here. Let's call this point D. So then when the length is AD, what is the resistance? Okay, as you can see. So that means our goal will be to see if I am plotting resistance in ohms versus length in meters, for example, will I get, according to this equation, a linear relationship? That means, will my graph be a linear graph like that? Okay, will I get a linear graph like that? And that's what you're going to investigate. Now, if I get a linear graph like that, because according to that equation, right, then see, then the slope, it should be a linear fit, right? And the slope A, that means if they're related directly, linearly, right, then technically this equation becomes R equals times some, slope, then times length. Then you can see, right, then this A, which is in this case the slope, will then be equals to the resistivity divided by area. Let me put it like this, area. And then finding the slope of this graph, you can then use that to find the resistivity of the material that we have. All right, so we're going to see that material that we're actually going to be using is going to be carbon, and we're going to use a carbon, let's say a wire, right, a piece, and then we're going to find resistance as a function of length. We plot it like this and find the resistivity. After we plot, find the slope. Remember, again, A here in this case is the slope of your graph of the resistance versus length. And then you should be then from here, find the resistivity. All right. So let's look at then the experiment. All right. So here's then the experiment, resistivity of a graphite. So we're actually doing graphite. So we're going to explore resistivity of a piece of graphite from pencil. Here's then, a video that pretty much demonstrates how we get, collectorite, right? How we get the graphite out of the pencil. Feel free to watch it. We don't really use anything from here, just basically for your information, right? So after you watched it, then let's say we collected our, let's say, wire of interest. That's basically our, the graphite, right, from the pencil. We remove it and we place it like that, and we're going to find then the resistivity of that. This is on the left side, right? You can see that's an ammeter. That's a device that's going to measure resistance. And our goal will be to take a measurements. By the way, there are, some questions that you need to be, answering. Again, this all based on the, the theory that I just explained. So think like this. The experiment here is this. You make a connection between points A and B, right? So then you can say, all right, so those are, if you're looking at this, here's the line. So let's say this is point A, and then this is point B. And then this is then the resistance of AB. And then this is the length AB right now. So you can use this ruler, place it like that, and measure the length of AB. Then after that, what you have here is you're gonna then watch the video where then we remove that and place it somewhere else. This is then point C. And then this is point D, and so on and so forth. And you can see, right, for every, new position, you measure the voltage, sorry, the resistance. Okay. So you're gonna measure the resistance, make sure that you take all the data points, right? So watch it all the way and get all the data points. You skip the data points, you're going to be losing points for that. Right. So as you can see, right. So all the way, so then that means, the idea is that we are decreasing the length and measuring the resistance. Again, according to this equation, resistance is equals to rho L over A. That means resistance is directly proportional to length. So then what we're going to do here is we're going to try to plot, right, the resistance versus length. And if they are indeed proportional, we should get a straight line like that, linear line. And that's what we do here is we have a data, length and resistance. So then you go ahead and measure that. So now, generally what we have here is this. So we're measuring the length using this ruler. And you can see, right, ruler is in centimeters. So let's say make sure you convert. Also, you can see that in a way, what we're given here is those lines technically allow us to make direct measurements up to that, let's say precision, like in terms of this is the distance, right? So this is 5, this is 6, which is 1 centimeter distance. Actual ruler gives you that as your, let's say precision. Any ruler that you have around you has a 1 centimeter, right, as a precision, because we don't have those dashed lines between them. Generally, what we can see then, the uncertainty in length is then 0.01 meters. Generally, this is the reading for the uncertainty of a regular ruler, because uncertainty is 1 centimeter, right? That's that that's the precision. That means anything beyond that we have to estimate, right? So anything beyond that we have to estimate. So we can use uncertainty as 0.01 meter or 1 centimeter. But this particular ruler allows us to even measure directly between the, let's say that. That means in a way, we can say that our precision can be, even half of that. So basically 0.005 meters. Okay. Now, the general rule is this. What you do here is you take the smallest direct reading you can get, and in a way, sort of like a divide that by 2 to get the uncertainty. So in a regular ruler, 1 centimeter is the smallest direct reading you can get. So half of that, which is 0.005, then is technically taken as a let's say uncertainty. So kind of like getting that in terms of this. All right, so that means now for this one, we get half a centimeter as a direct reading, right? Then half of this 0.0025 meters will be then uncertainty. Okay, because we are estimating, right? We are estimating technically if the reading is somewhere between. So what you need to do here is you need to make another table, right? And then put, like, let's say this is uncertainty, right? Uncertainty of your length measurement. So resistance, you can, skip the doing the uncertainty for that. But here we need to do then uncertainty of the, length. Okay. And then we can just assume that, all right, so since it's the precision is going to be precision of the instrument, so they're all going to be 0.0025. That means all of them going to be pretty much 0.0025. Okay. Then what you do here, you make the measurements, right? So I don't want to, populate this with the data, data, because you have just one trial. I don't want to make the measurements for you guys. So, but measure the length, initial length, and then resistance, initial length, resistance, and then all the way until very last, measurement. And then here you're going to do then plot resistance versus length. And then here, when you do the resistance, make sure then you are clicking the uncertainties. So see, if you click this, you then clicking uncertainties, then it will give you those error bars as well. Okay. But it's a straightforward, graph, length, resistance, and then you get your, a plot. And then you go and curve fit. That means if everything, should match, then y equals ax should give you the right, fit. And then when you come back over here, this should be then your slope, which then you use to find the resistivity of graphite. And after that, there are some questions based on your experiment, based on the theory. And I imagine most of them you can answer in terms of, let's say, the equation and everything I provided in this video. Um, One thing I want to point out here is that you remember, for all the calculation, I need to see your work, and there are two things you can do, right? You can put all your work on a separate piece of paper and upload it, or you can just use this box, right? So let's say, and provide, it says show how you can use the slope of the line on your graph to find the resistivity. So that means I want you to talk about and show me the derivation based on what you can then make that, let's say, calculations. So there are two things you can do, right? So you can either put everything on a small piece of paper and then take a very low resolution picture, because now for some reason, if it's a high resolution picture, and most of the phones right now take like, 4, 5, 10 megabyte pictures, we don't want, so the lowest possible resolution, or, convert it back to low resolution, right? Small, size file, and then upload the picture over there. Or I can provide, there's a latex code that you can use that here when you're typing that, in order to, include your equations and Greek letters and, anything like that. That means, there's a latex code that you can use to do some of those things. So, and that basically can allow you to just directly here type, let's say some of those, let's say codes, let's say, in terms of the values that you have. You can just basically do it in terms of equations, in terms of numbers, in terms of, let's say, those Greek letters. So for example, let's say, if you want to have a row, right, which is a Greek letter. So how to do row? So you go, so let's say here you do backslash and just row. Sorry, not here. So you click it here. So backslash row, and then see, it gives you row. Okay. So it allows you to pretty much, get some of those mathematical. So you can say, for example, if you want to write this, so you can say, all right, so resistance equals to, then let's say you do backslash row times, um, for example, then multiplication will be backslash c dot. Then this is basically row times length. Then we're going to divide that by area, right? So then we do backslash uh, div, division, and a. And if I click this, let's see, it didn't work. All right, so let me try again. So you can do this. So r is equals to, so r is equals to, then backslash row, then space, then backslash c dot, space, then length, then space, backslash div, which is division, space, then a. So you get something like this. There you go. More or less, in terms of putting in mathematical way like this. You can do a, as a fraction, like let's say L over A. Well, that's another latex code. Again, I will provide that code. If you want to work with that, uh, and use that, by all means. If you want to do by hand, you can also do that as well. But that's what we have. So use that uh, data, plot the graph, use the slope to find the resistivity, and then after that, you should be able to answer all those questions at the end.